Today we're going to cover session 2 of the benefits of Fabric and ongoing administration. Today we'll cover Fabric and the security concepts behind it, and we'll go into some detail in that area. Not too much deep in the weeds, but at least enough that you can get the idea how it's different than everything else out there today. So once again, my name is Jim Clark. I'm a senior systems engineer for Extreme Networks, and I have Constantine Romano joining me today as well. Actually, FCG is running this, but Constantine, introduce yourself and
Uh,
we'll kick it off.
Thanks, Jim. This is Constantine Romanos. I'm a senior solutions architect at StepCG.
Okay, with further ado, let's get running. So far this has been the agenda. Last week we covered the Fabric fundamentals. As I mentioned today, we'll cover the Fabric and security, and then next week we'll do some more advanced concepts, which will be the third and final session of this webinar series. So just for some background from where we left off last week, kind of looked at conventional networking versus Fabric, SPV, short path bridging, MAC encapsulation. You'll notice up top there we have we're showing some switches with some VLANs, and if you want to do a layer 2 network, legacy wise, you need to create the VLANs on all the switches, tag those ports, worry about spanning tree and things like that to make sure that you don't loop the network somewhere. Somewhat tedious, if you would, as we mentioned last week. And then if you look at the bottom, under the bottom, the Fabric way that SPV handles it, Fabric Connect. Fabric, as we mentioned last week, is we configure that at the edges. So only the nodes that you see configured there, and the one on the left and one on the right, get the VLAN configured. We use an ISID, inner source identifier, that kind of ties it all together. You'll notice that we use 20,010. We mentioned last week that we have anywhere from 1 to 16 million ISIDs that we can use. So no longer are we VLAN constrained. So we can use VLANs over and over again because those VLANs become only local significant at the BEBs where they're configured. So as we mentioned last week, it doesn't matter how many switches we have in the middle of that Fabric core there. It could be 1, it could be 1,000. We just configure the VLANs at the very edges and assign it the ISID, and the rest of those switches in the middle just transport that VLAN across there using that ISID. So once again, that edge provisioning, very simple to do. Basically just one line or so just to configure that, and away you go. So that's basically the conventional versus Fabric-based VLANs assignment there. So, and then moving on, once again, for further review from last week, there's ways to do, tunneling that VLAN, so you do get it across there, but it's going to ride on top of IP. As you know, the conventional way out there today, you're going to use either VXLAN or a GRE tunnel. It's going to be based upon some routing protocol, so you can once again assign those VLANs at the very edges, but there's a lot of complexity there in the middle where we have to worry about routing, things like that. So every switch in the middle, no matter whether it's 1, we're showing 1 here, but what if it's 10, 15, 20, whatever? You need to create those tunnels across all those routers. So a lot of complexity there, a lot of configuration, a lot of room for a fat finger that you could, do something wrong there. Once again, with Fabric, because we're going to do it at the edge, you can really only affect those edge ports there. Down the bottom, once again, we're showing how we just configure it at the edge, kind of like the last slide, and we just configure at the edge. So once again, it's edge provision. We're also showing that we're talking VLAN 10 to VLAN 11 traffic there. Kind of the cool thing with Fabric is because the VLAN is only local significant, we can assign that ISID, and that ties those VLANs together. So it doesn't matter what the VLAN ID is. Those two VLANs will communicate with each other across the network. Once again, the switches in the middle do not participate in that security zone, if you would. We're going to talk a lot about security zones today, and we'll mention the phrases of virtual service network. The service can also be interpreted as a security zone, so kind of interchangeable there. But you'll notice down the bottom, doesn't matter how many switches are there. The switches aren't a part of that zone, so it's traffic in the night, ships in the night, traffic that they can't be a part of, they won't see it unless they're configured. And I think last week we also mentioned that the traffic is configured on a BEB, backbone edge bridge. There's also the switches in the middle called backbone core bridge. So we went over some acronyms last week. Once again, to review that, the backbone core bridge basically just is a transport mechanism. It does not have any services assigned to it. Once you assign a service to it, it becomes a backbone edge bridge. So really just minor differences there in how they handle traffic. A backbone edge bridge can still transport traffic, so it doesn't have to just stop transporting other traffic to other nodes inside a network. So it can kind of act like a pseudo BCB. If it doesn't need that service on it, it can still transport the services across and not see those services as well. So some terms there. So we also mentioned last week, typical routing, conventional way, VLAN 11 needs to talk to VLAN up top there. So we need to have some routing protocols in the middle there. So they transport that routing table across all those different switches. Each one of those switches has the route table in them. So they can route those tables. And if you do a show IP route, you'll see the routes show up there. So then, 10.1.2 can talk to 10.2.1 network, and we're all happy with that routing protocol. The fabric way to do it is we configure that the VLAN on the left there, 10.1.2, edge provision. Once again, we go across the network, we create a VLAN 12, 10.2.1, and it transports that network across there. It's pretty cool that we didn't talk about this last week, but when you do in this scenario, if I do a show IP route, it's one hop, and I don't care if it's one switch in the middle or 30 switches in the middle. It's one hop end to end. It's on and off the network in this particular diagram. So when those switches in the middle do not participate in that route table, they do not see it. They have a mechanism called an IP reachability, so they know where traffic needs to go to, but they do not see the traffic. So if I do a show IP route on any one of those switches, the route table will be empty in those backbone core bridges. So we replace OSPF with that, with this IP shortcuts. We can redistribute any routing protocol into IP shortcuts. So if you have a network, a legacy network, OSPF, BGP, you name it, we can redistribute inside of Fabric Connect, inside of IP shortcuts, so that you can see those routes and you can transport those routes. We have a lot of customers that had legacy OSPF networks and still do today that need to transport traffic in and out of OSPF, other routing protocols, et cetera. So you can still do that very simply. And in this particular situation, a VSN is not needed or required, but it's typically just a route table. So, Constantine, anything to add on this slide?
Yeah, thanks, Jim. So I really do like this slide because I think it does a really nice job of representing the way that IP shortcuts and the global routing table kind of implements routing in a way that's integrated with ISIS and shortest path bridging, rather than it being protocol layered upon protocol, right? So IP shortcuts is integrated with shortest path bridging. You don't have to say, oh, am I going to use OSPF here? I'm going to use RIP here. What does this switch support? What does that switch support? It's a fabric network. It supports shortest path bridging, and it's as automatic as you can get with populating routing tables. So, yeah.
Great point. So, I mean, we mentioned last week too that we separate the data plane from the control plane. So ISIS is that control plane. So the data plane never sees a control plane. So that's another key that we mentioned last week. So just as for further review. Constantine, why don't you jump in and take this slide here? We got some configuration.
Absolutely. Thanks, Jim. Okay. So here we've got a couple of just configuration examples of how we handle native routing over SPB and IP shortcuts. In this case, IPv4, which is what the vast majority of all the enterprise networks that we're going to work on are going to be using. You see the basic configuration lines up top, loopback, VLAN creation, adding ports, routing the ports, of course, because it's a backbone edge bridge. So we're mapping, if we want to circle back to our earlier session, the backbone edge bridge is where you map the IP, I'm sorry, the VLAN to an ISID to route through the to advertise in the network. And then we go into router ISIS. We tell it what the source address is. You'll note that the source address is the same as the loopback in this instance for both sides, 10.00.13 and 10.00.14. So when you look at the routing table, the next hop address is going to be that IP source address for all subnets that are handled or routed through that particular distribution layer switch. So when you hear distribution layer, that's the functionality that we're talking about, right? So you see it's very, very a small number of configuration, small number of configuration parameters to enable IP shortcuts globally, right? Router ISIS, source address, enable IP on the SPBM instance. You tell it to redistribute direct routes, right? So that's basically any routes, any subnets that are local to that switch, it's going to redistribute into the fabric. We enable the redistribution, and then we simply apply what we've done. And within seconds, you start seeing the global routing table getting populated. Jim, anything you want to add here?
No, that's perfect. The description there. Yeah, absolutely.
Very good.
Go to the next slide. So once again, continuing on here. So so this, I think this slide. Go ahead. Again.
Oh.
Yeah. No. Yeah.
I'm sorry. Yeah. So we're going to extend now that conversation right to multicast. Now we've got our layer 3 network set up. Now we've got to do multicast over it. And traditionally, when you were doing multicast, you would have, again, a layer 3 protocol, OSPF, might be RIP, it might be something else. Most commonly OSPF these days. And then you have to configure PIM SM on top of that, which can be very complex and easy to get wrong. With multicast routing over SPB, we no longer have any need for that. We don't need a specific virtual service network for multicast. It's not constrained. IGMP is only at the edge because it is an edge feature, so we don't have to worry about having to implement IGMP throughout the network. It's simply going to be between the backbone edge bridge and whatever the device or node on the edge is going to be, with PC, camera, DVR, whatever that might be. And again, the routing from that point forward is single hop for multicast, just like it is for regular layer 3 traffic. So
just add on to that. Last week we kind of mentioned that we mentioned protocol independent multicast. We're showing up that conventional slide up top there, where it really needs to ride across a routing protocol, as you mentioned. But we also showed last week how it's kind of like a stack of cards. If OSPF dies, your multicast dies. So think about that if I'm in a high security area with cameras and like airport, for example, and my OSPF drops because of some loop in the network or something other issue, or I fat fingered something, that brings down not only the routing protocol but also my cameras, my multicast traffic. So it becomes a house of cards where everything falls apart. Add on, protocol independent, multicast requires a bunch of configurations like a rendezvous point, bootstrap router. There's some new features like auto RP that kind of does things for you to some extent, but a lot of complexity because every router has to be configured with that multicast traffic, where once again down the bottom we configured at the edges. It's really just one command at the VLAN level, and the way you go at a layer 2. So when you think about multicast and fabric, it's always at a layer 2. We can constrain across different service mechanisms like layer 2 virtual service networks or layer 3 virtual service networks, but it is once again provisioned at the very edge and is constrained within inside of those zones. So as I mentioned, some very short configuration. So really, you go into router ISAS, you tell it that you want to enable multicast for SPB1, the first instance of SPB, and then you go into the VLAN and say IP SPB multicast enable. 2 commands, and that VLAN is ready to go, rocking and rolling with multicast. Constantine, anything to add on that slide? Not a whole lot there, so pretty simple.
Yeah, there really isn't, Jim, as you point out. So, but if you want to click over, I do want to bring up that next graphic about the PIM configuration. So
let's configure, move on with that a little bit. I think I mentioned some of these things already. So we're showing here a bunch of different nodes, somewhat of a larger network with some core switches in the middle. Once again, we're showing ISIS as that control plane to transport the traffic around the network there. We're showing some cameras there and some receivers, being the PCs there and part of the pictures. But so the multicast stream is received at the edge. So the sender starts sending that multicast traffic across there. It automatically assigns an ISID. In this instance, it would be actually the 8th instance. Because we typically start at 16,000,001, so this would actually be the 8th instance of the sender. So it starts sending traffic, and kind of much like PIM, where if I don't need to see the traffic, I kind of send it out and then I kind of prune it back. But the traffic is always known by the nodes, so it's kind of there. It's dynamically mapped as a new service, and the ISID kind of forms that source in the sender group scenario. So an ISIS advertises that across the whole network so that every node will see it and can be a part of the stream. You'll notice here that the sender on the left here sees it, joins it up. So now that traffic is sent to that BEB switch there on the left-hand side there. As more senders look for it around the network, it gets sent to each one of those senders. But you'll notice that under no circumstances is the traffic sent to nodes that aren't required to see that traffic. They're not asking for it, they don't see it. So the BEVs won't send it out, or the backbone core bridges will not send it out. There's really no need to prune it if somebody drops off, but once again, with shortest path bridging, if a node dies somewhere in the middle, it will still take the shortest path to get to those receivers, and the traffic will not drop. If you know anything about video traffic, typically it's the most the traffic that you'll notice dropping the quickest, because you'll see pixelizations in your video traffic. Typically with Fabric Connect, you may see 1 pixel drop, but typically you won't, even if you use the whole node. So you might, like the worst case scenario, you're going to see one pixel drop, and then it'll join right back up again, because it'll grab that next shortest path. And since the traffic is already known by those other additional nodes, the traffic's already there, ready to go. So it just gets sent on, and so very, very fast recovery in those scenarios. Constantine, anything to add on this slide?
Yeah, just wanted to talk about it in kind of in a real world type scenario, what that pixelization might look like. If you've got a cable TV service, and sometimes when you switch channels, right, and it takes a minute for the video feed to come up, and it comes up highly pixelated for a few seconds until it fully forms. That's what you're talking about. You're basically joining a multicast stream at that point as you do it. So
yeah, good point.
Okay. But yeah, let's go ahead and grab the next slide, Jim.
Here we go.
Thank you very much. So talking a little bit about conventional networking again versus Fabric. So up until now, we've talked about basic services that we configure to implement Fabric in most networks, including most school networks, right? ISIS, sort of shortest path bridging, the global routing table, and multicast management. As we move forward, we'll be discussing a little bit more advanced features that are going to be more use case specific. So it's still important to discuss them because they still apply to the general fabric infrastructure. And they do also very much apply to how fabric enables and facilitates higher security networks as well. So
Yeah.
we're going to talk about layer 3 VSNs, I believe we're going into next, correct?
Yeah, correct. Let's just add on. So this is, security segmentation are mainstays of Fabric Connect, because of how we break down those security zones, those virtual service networks. Once again, those two, in my mind, is both of those statements are interchangeable. Whether you're saying a layer 2 virtual service network or a layer 3 virtual service network, think of those as security zones. Segmentation, how we segment traffic. The more I can segment traffic, the more secure I get. We've had multiple hackathons that we brought in MIT, Dubai, Russia, et cetera. Individuals from Russia try to hack Fabric Connect, and it has not been hacked yet. So if you set it up right, it's going to be very, very secure. And once again, you're going to create those security zones to separate all your traffic. So you'll hear us talk about security as we go forward in this presentation. So looking at this slide here, you're up top there, you're seeing conventional Fabric Connect. We're going to compare Fabric Connect layer 3 virtual service networks to MPLS based upon IP VPNs. You'll notice that once again some complexity here, but you have tenant A on the left there, tenant X as a tenant A would be green MPLS, and tenant X and would be red MPLS based IPVPN. Those two traffics are separated, but they're separated based upon the LSPs there, the tunnels that are riding across the MPLS backbone, based upon another routing protocol like IBGP, et cetera. So a lot of complexity there. A lot of configuration parameters, a lot of room for fat fingers, and once again, we mentioned that multiple times so far. If you look down towards the bottom of the slide here, where we show Fabric Connect, we still give you that same service separation, security separations like you do up top, except for we configure those services at the very edge. So you'll see tenant A is still part of green. They're combined together using an ISID. In this scenario, ISID 200. Up top and down the bottom, you have the red security zone based upon ISID 300. So A can see A across there, and once multiple networks, it could be multiple 10.1, 2, 3, 4, you name the networks up top there, but multiple networks inside of those, inside of green, that they're all going to route to each other, and you configure your networks accordingly. So depending on how many networks we're showing one here, but it could be hundreds of networks, but they're configured inside of the green network there, the green virtual service network. Down the bottom, we're showing red, the same thing, multiple networks. They're constrained by their ISID, so that green cannot see red, and red cannot see green. And you'll notice it's so differentiated that we can actually use the same subnets. So you'll notice that green is using 10.1.1, and red is using 10.1.1, because these are two separate routing forwarding tables. VRF is virtual routing forwarding. So these are two total separate routing tables. But in the Fabric world, we can configure these services very easily, the security zones very easily. Just a couple of parameters. The complexity is not there because we're doing nothing in the middle. Once again, those backbone core bridges or even some backbone edge bridges, it's become transport for these layer 3 virtual service networks. No need for MPLS down the bottom there. It's just Fabric based upon the one protocol. So no multiple protocols needed. It's all embedded inside of the one protocol. As we mentioned last week, IEEE and IETF ratified short path bridging based upon how it transports services, and everything was based upon one protocol, so no multiple protocols. we also mentioned last week that, with the way network has grown, you added on OSPF, you added BGP, you added PIM, et cetera, VXLANs, et cetera. You kept adding on protocols to solve multiple problems. But in the short of edge bridging world, we handle all those multiple problems with one protocol. Constantine, anything to add?
Yeah, absolutely. Thanks a lot, Jim. So a couple things. I think one of the things that this slide really represents very well is simplicity versus complexity, right? The conventional method, MPLS, MBGP, IBGP, has a fair amount of complexity to it, has a fair amount of complexity to configure it properly. And if you think of security as a function of simplicity, right? The simpler it is to implement, the less likely it is that a mistake will be made that's going to violate your security requirements or standards, the better off you're going to be, right? So as Jim mentioned, VRF stands for virtual routing and forwarding. In the industry, a lot of times you'll hear that just referred to as a VRF, because we like to do things like that. So what that fundamentally means is that your physical router, switch, network device is subdivided into providing virtual routers. And the virtual routers do not talk to one another unless you explicitly tell them to, right? So in the instance where you've got in the bottom part of the slide, where you've got the L3 VSN 200 and L3 VSN 300, those are two separate routers, and those separate routers are virtualized, and they will traverse your entire network, right? And they will not talk to one another. Even though you may have multiple switches participating in them, you will not get any crossover between them. So from the standpoint of security, I think it becomes very, very clear how that can be beneficial. You certainly can route between them. If you wanted to, you would have to create policies to do that, but in a multi-tenancy environment, you wouldn't necessarily, right? So that's kind of the key point here, right? Security through simplicity.
Absolutely. Great point. Yeah, just to further to kind of define this, so you can wrap your head around it. Those switches on the left and right there down under fabric, just kind of view them as being, even as one switch, you can actually view them as like they're kind of like separate switches, if you would. So we can create 256 VRFs. So you can kind of divvy that one switch on the right and left there kind of 256 times if you wanted to, with 256 totally separate route tables. And but very simple to do. Multiple ways to have those different red and green talk to each other. Firewalls. You can do some policy things like that. We can leak some of those, not really leak, but we can combine them through different ways. What we would actually call an inter-VSN, inter-virtual service network, so we can kind of combine them and whatnot. So we can totally keep them separate or combine them, but once again, very simple to do. So security through simplicity, as Constantine mentioned. So just continuing on here with that same concept here. So we're showing, once again, that typical map we've been showing. So each one of these ISIS switches at the control plane, with the data plane, it advertises all the services across the network. So we're seeing a bunch of green networks as well as a bunch of red networks that are scattered throughout the network, but provisioned at the very edges here. So all these different security zones are again, provisioned at the very edges. So the switches that are involved in green see green, switches that are involved in red see the red route tables. You notice the one on the left-hand side, the two on the left-hand side actually have both tables in them. So there is no rule there that you can't have that. Obviously, you're going to want that as you go build it. But you're noticing also on the right side there that only some switches have green and some switches have red. So there is no rule on how we define or where we send these L3 VSNs. across the network. But all the switches will get advertised so that anything with ISID 3001 or 30,001 will see those routes. So if I do a show IP route at subnet A there on that switch on the left there, he's going to see C and D and also B down the bottom there. So he's going to see all those 4 different subnets. The same thing would be true for ISID 30,002. All the switches are going to see subnet X, W, Y, and Z, so that all the route tables are joined there, and they can all see each other, so the traffic will flow on each one of these different security zones. Anything to add there, Constantine? It's one hop for everything. So if I'm on subnet A, if I want to get to C, it's one hop from A to C, one hop from A to B, etc. So no matter how many nodes in the middle would fail.
So one thing I just wanted to add, just like we talked about with the layer 2 VSNs previously, about how you create a VLAN, you map an ISID to it, and then that ISID is advertised, not broadcast, but advertised throughout the shortest path bridging network. And any switches that have that ISID provisioned will automatically form tunnels to connect and create those services. The same exists in a layer 3 VSN or a virtual router instance. So, and we're going to see in the next slide, from a configuration standpoint, it's conceptually identical to what we were doing with transporting a VLAN across the fabric, except now we're transporting an entire virtual router across the fabric. We're simply going to create the virtual router, assign it an ISID, and once we do that, again, that ISID is going to be advertised, and that ISID is going to be going to enable the tunnel building across switches. And one thing that I like about this slide is that it kind of shows you how the layer 3 VSN, the virtual router, will exist throughout the network, and those tunnels do get built in an automatic way. So thanks, Jim.
Yeah, no, so yeah, once again, just to further define that. So ISAS is the advertiser. Once again, that control plane is the advertiser, but not a part of the data plane in that scenario. Just it's going to advertise it, but will not see it unless the service gets confined there, like we're seeing on these different green and red nodes there. Let's move on to the next slide. So just configuration-wise, this is how we configure L3 virtual service network. Once again, security network. You'll notice that we have some VLANs created here on the left and the right-hand side there, edge provisioned. We're showing the green configuration, 30,001 ISID up top there. So 10.1.101 and 10.1.102 are the VLANs, and we assign them to a VRF green. Excuse me, the VRF name can be anything. You'll notice up top there, we're giving it IP VRF green, VRF ID 1, so it's the first instance of VRFs. As I mentioned, we can have 256 of these. It could be called Skynet, whatever you want to call VRF Skynet, whatever. Typically, that's what I use in a lab, kind of after the movie there. So we tell the VLAN that it's a part of VRF green, and as soon as we do that and give it an IP address, it creates that subnet 10.101 inside the router VRF green. So we take it from the global routing table into VRF green routing table. So 2 separate route tables there, even at that level. Down the bottom, we go into router VRF green. We tell it that it's now an IP VPN. We give it an ISID. We tell it to enable it. We redistribute it inside the VRF there and apply it, and away we go. So really just 6 or 7 commands there to get it working. Very simple to do, unlike the complexity of MPLS as we showed last week, where you have probably like 20 some lines of code for every switch you got to do this on. We're really just showing 4 or 5, 6 commands here, where we're assigning each one of these different nodes that only need to see it, like as we show here on the left on BC, on the BEB-C and the BEB-D. So the one, BEB-G does not need to see the traffic, so not a part of the security zone. So ISAS just transports that traffic across there And once again, that traffic is secure across the fabric, and only the nodes that are configured it are going to see it. Anything to add?
Yeah, I mean, actually, I really don't. I think this is a great slide to illustrate how the how the VRF tunnels are configured and built. Thanks, Jim.
So, last week we were talking about the control plane of ISIS. We kind of just want to back into that a little bit as we get further into those layer 3 virtual service network configuration parameters that we're going to go over here in a few minutes. We noticed that, last week, the control plane, what is it? We use ISIS. We kind of just use that as an acronym and well known, but some people may not know what it stands for. So intermediate system to intermediate system. It's been around for a long while, but really hasn't been used to its full potential because it can handle not only layer 3, but also layer 2 as a transport, which is exactly what we're doing inside of SPB Fabric Connect. It's a link state protocol, so if a node fails, every node knows where they are based upon the ISIS link state database. So if a node fails, it's automatically recovered. So we can give that sub-second. We're showing 200 milliseconds here, but it could actually be as low as 50, etc. So very fast convergence. It's a dynamic routing protocol, much like OSPF, but because it uses shortest path first routing algorithm. But once again, it doesn't have to build a route table like OSPF does. So it automatically comes right back up again. So if it dies, if it gets a link flap or whatever, it's going to drop. The route's going to get moved to somewhere else and not get moved back until that route is stable. Mention's been around for a while, 1987, 1988 scenario. So one of the first protocols, but as I mentioned, not really used much. Industry kind of skipped over it, added on OSPF version 1, 2, etc. as we're showing down the bottom there. But once again, wasn't really used much in the past there. So we're going to kick over now to some examples of fabric provisioning. So Constantine, why don't you jump here and then kind of lead some of these slides here, and we'll move through these configurations.
Yeah, thanks, Jim. So, folks, what we're going to do in the next series of slides is we're going to kind of go through the building blocks of how we go about configuring or building an SPB network, right? So, pardon me, slide 50 here that we're looking at is the basic configuration parameters, and we're not going to go through each one in detail, but I do want to kind of go through the individual commands, at least for one switch, right? So the prompt command is not really necessary, but that's where you name it, right? You go into SPBM, router ISIS puts you into the ISIS router instance. You assign a system ID. We talked a little bit about system IDs in the previous session. System IDs can be generated automatically, so you'll notice that that's highlighted in orange there, but we recommend that you do it manually, right? Because for better manageability of the network. But if you want to go with the automatic assignment, you can certainly do that. Everything that's highlighted in green can also be auto-generated with zero-touch fabric. Which we haven't really talked about in great detail. That is a newer feature that's been rolled out in the later versions of the VOS operating system. But we're going to go through them anyway because it's important to understand what's happening underneath under the hood, even if you are in a zero-touch type environment. So the manual area is assigned. You go into the SPBM instance, SPBM1. That is the default. Some of the switches, by the way, do have the ability to have multiple SPBM instances, multiple areas, but for what we're looking at here, we're really going to be just sticking with one that fundamentally is the vast majority of the networks only need. one SPBM area. You assign a nickname, assign the primary and secondary backbone VLANs. You then create them. You enable ISIS. CFM SPBM MEP ID, that's in orange, that is optional. CFM stands for Configuration Fault Management. So that's a troubleshooting method that we have access to. You don't have to use it, but it's a good idea too. You'll also notice there in that MEP ID 41 that the 41 is highlighted, and it's also highlighted up on the system ID line above that. A reason for that being that you want to maintain consistency. You don't have to, but it's certainly a good idea too. So you'll see where it says system ID and it ends in a 4100. You see where the SPBM nickname ends in a 41. You see where CFM SPBM MEP ID is also 41. Those are unique values that are assigned to that switch, and if we maintain consistency, we can also prevent a great deal of confusion. So. Jim, if you want to run through or add anything on this?
Yes, so I guess I would just add.
Had our door decorating contest in place this morning as far as.
Mute that. You know, just add on there. So that system ID is unique across the board for every switch. So that is unique, and as Constantine mentioned, somewhat, you know, make that consistent if you can, so you kind of know where it is. But if you do a show ISIS link state database, LSDB, you'll see these nodes would show up, and you'll see that system ID as well as the nickname, and depending what command you're running to show your fabric. But yeah, great definition here, Constantine. You did mention zero touch fabric. These switches now, when we ship them with 8.3 and above, we're on 8. We're getting ready to roll 8.5 out here shortly, but 8.3 was a feature we called auto sense. So basically, you take a switch out of the box, plug it into another fabric node, and it'll automatically come up and be part of the fabric. It'll even grab a management IP address for you, so you can get to it. So you can really have anybody install these switches now. You can have a third grader walk it down to a closet, plug it in, and away you go. So real simple to do now. But as Constantine mentioned, we like to show what's really under the covers, so that you know what's happening here. So let's move on.
Terrific. Thanks, Jim. So so the SPB interface config. So in the previous slide, we created our basic SPB configuration parameters, right? So we enabled and configured shortest path bridging on the switch globally. Now we're going to go down to the interface level. And again, a lot of this stuff is going to happen automatically through zero touch, but looking at how the engine works under the hood. And again, I'm only going to go through one of these text boxes here, but again, you go into the SPBM instance. You do, or I'm sorry, rather you go into the particular interface. So if you look at the diagram revolving around VSP 4000-1, its uplink into the core is 1/12. So we're going to go into interface 112. And we're going to enable ISIS. We're going to put it in ISIS SPBM instance 1. In this configuration example, we're assigning a layer 1 metric to it. You don't have to do that, okay? But it's helpful to do, especially if you have multiple ISIS links of differing speeds. It's very important that you assign the metrics so you don't get weird and low speed data paths being prioritized. Okay. The hello auth type, again, that is an optional parameter. But the ones that are not highlighted in orange, those are the fundamental ones, right? So ISIS is PBM1, where you're adding the interface to the particular shortest path bridging instance, and then you enable ISIS, and that is all. And you do the same thing at the other switches, and you start seeing, at this point, you're going to start seeing adjacencies form and the fabric starting to come together. As the switches form their adjacencies, as they start advertising services to one another, etc. Jim, anything you want to add here?
Yeah, everything I'm at was like we've been showing a single link between each switch up to this point in time. You could have multiple, for example, you can have multiple from 4001 to 4002 up top there, and we could either trunk them together, or we could actually have different speed-based interfaces where you may want to use a 100 gig, for example, versus a 1 gig. So if the 100 gig drops out, the 1 gig is ready to go and just picks right back up with the shortest path scenario. Or since it already would be active in that scenario, but just the traffic would automatically just go across it. So we've been showing one, but there's multiple ways to do this. So every switch can have a trunk of 8 or 8 different interfaces if you would. I'm not sure why you would really do that, but you could. You might have 8 different carriers, for example, and go across the carrier network and just have these nodes all connected. Or around your campus environment, you could have multiple different ways to get to a building, et cetera. So we've been showing one, but you can actually have multiple interfaces there. But and if you did that, you'd probably want to use the metrics here to define what they are. But as Constantine mentioned, you do not need to use the metrics, but you could use that for traffic engineering, of course.
Hey, thanks, Jim. So, and now we're going to move on. Now that we've formed our fabric, or we've done our basic configuration on the switches, we've formed the fabric in the previous slide, and we've formed the adjacencies. That is to say, the switches. So when we say adjacency, that means that the switches can see each other. They're exchanging SPBM identity information with one another, and the fabric is formed, right? So the fabric is formed, but there's really nothing we can still do with it, right? Because at this point, we've just got a bunch of switches that can say, okay, yeah, I see my buddy, good, I'm good to go. Now we got to run services on top of that, right? Again, what you see highlighted in orange is optional. And I'm going to go through the VSP 4000-1 configuration here. Interface loopback 1, we've already seen that, of course. It has an IP address, router ISIS source address. So that command tells IP shortcuts what the source address is that it's going to use to advertise its layer 3, its VLANs, or its more correctly, its subnets into the rest of the network. So telling it the source address is the loopback address 10.0.0.41. The optional IPv6 stuff we're going to skip as part of our discussion here, and then we're going to go into SPBM1 IP enable. SPBM1 IP enable basically says tells the router to participate in the local the local routing table. So whether you're doing layer 2 VSNs, layer 3 VSNs, you need to have all this. IPv6 is optional. You'll notice there's a node here called the backbone core bridge, the VSP 4000-2. If it's not providing any services, it doesn't really need a source address. If there's no ISA to VLAN mapping, if it's only acting as a true pass-through switch, still needs a loopback address just for management. So, okay. Jim, if you got anything to add there?
No, well done. Let's move on.
Okay.
So as we look at the configuration for layer 2 virtual service networking, service security zone here, we've kind of been talking about this, as we start even the session today. We've been pointing out that VLAN 10 is assigned to VLAN, ISID, in this scenario 200,010. Once again, we can use any number we want to for that. But we're showing provision that 4001 and 4004. and also 4000 and the bottom one. I guess that would be an edge node there using fabric attach. But we're showing once again provision at the edges. Really just, you create the VLAN, give it an ISID, and the L2 VSN is created no matter where you do that. So we're just showing that 3 nodes here are configured. Down the bottom left there, that would be a fabric attach base, which is really just like an edge switch. We're showing an XOS switch, version 2, G2 of that. Can be any one of the newer XOS as well, the universal switches, the 5520s, the 5420s, et cetera. Any one of the switches can do that as well as be a part of the nodes, the fabric, depending on how you configure it out of the box. But excuse me, but really 2 commands to get that layer 2 network working there, and then the security zone is transported across the network. We see this type of layer 2 services networks used in scenarios of, payment card interactions, HIPAA, things like that, guest networks, things like that, as we mentioned last week. Can I see anything, Nat?
No, Jim, I think this is a great slide.
Okay, then moving on with layer 3 virtual service network security. That we've been talking about security all day long here, but just to really break it down a little bit more, what's required to create that layer 3 virtual service networks. And you'll notice that even though it's a VRF green here, we really just need to configure it on the nodes that need to be a part of that security zone. We're showing VLAN 101 talking to VLAN 102, to 2 different subnets. And so we start out by telling the routers, both 4001 and 4004, that they need to be a part of VRF green, VRF instance ID 1, and then we go into router VRF green. We tell it that it's an IP VPN. We give it an ISID, and then we enable that IP VPN, and we redistribute it. And voila, we have a route table on those 2 switches will show up, and they'll be able to ping back and forth and see traffic back and forth, no matter what that IP traffic is. So real simple to do. Really just 6 commands there, really, and that VRF is defined and ready to go.